Okay, I'm going to launch into Module 20 to 24 lectures. Um, just to give you a heads up, I'm going to record essentially the lectures that I give in my summer class, which is why you'll see up in the top corner here the designation that it's for my summer class and when in my summer class it falls. You can ignore those, but that's just evidence that these are lectures that are given in a college organic chemistry class. Um, the order might not be exactly the same as the order of the modules 20 to 24, but the information in this series will cover all that material. Um, so if you watch these, you'll have everything you need to know for modules 20 to 24. Um, so modules 20 to 23 really are dealing with reactions of alkyl halides. You've already been introduced to alkyl halides as a functional group, and in this course you've already been introduced to how to name them. So I'll start with just a reminder of how you actually go about naming alkyl halides. You already know these, so I would recommend pause right now, try and fill in the names for the structures where no name is given, like this one and this one, and try and fill in the structures for the ones where a name is given. So you're filling in structures there. So pause, try and do that for yourself. It's a good review, and then I will walk through naming these. All right, so remember for naming, you're always going to start by numbering your chain, making sure you find the longest carbon chain. So for this one, I have 1, 2, 3, 4, 5, 6 carbons. So I know this is going to be some sort of hexane. I could number it in the other direction, but if I number in the other direction with the blue numbers, then my numbers will be 3 and 5 rather than 2 and 4. So I'm going to keep the red numbers because that gives me lower numbers. So I said this is going to be a hexane, so that's the end of my name. And then the two substituents are chlorines, so those are going to be named as chloro groups. There's two of them on carbons 2 and 4, so this is going to be 2,4-dichlorohexane. For the next one on the bottom left, 4-chloroheptane. Heptane means I'm going to start by drawing a 7-carbon chain. 1, 2, 3, 4, 5, 6, 7. And I'm going to put a chlorine on carbon 4. Okay. This next one, I have a 5-membered ring. So this would be 1, 2, 3, 4, 5. 5-membered ring, since it's a ring, it's going to be a cyclopentane. All right. And then I have on carbon 1 a fluoro group, on carbon 2 a methyl group. So this will be 1 fluoro, 2. Oh, and I have the luxury of moving this down to give myself some more space. 1 fluoro, 2 methyl. Cyclopentane. If you did module 8, then you will notice that there is stereochemistry to consider here. So on carbon 1, I have a fluorine, which is going to be my highest priority group. Then the carbon with the methyl group will be second highest priority. The carbon with no methyl group will be the third highest priority. So I'm going clockwise. Hydrogen is pointed back, so this is going to be R. So we would have 1R. And then carbon 2 There, the carbon with fluorine is going to be my highest priority. Carbon in the ring is going to be second highest priority. The methyl group will be third highest priority. There I'm going counterclockwise, but hydrogen's coming forward, so that is also going to be R. So 1R, 2R, 1-fluoro, 2-methyl cyclopentane. And then this last one, okay, I have a butane, so I'm going to draw a 4-membered chain. 1, 2, 3, 4. It's 1,2-dibromo. So on carbon 1, I'll have a bromine. On carbon 2, I'll have a bromine. And then 2-methyl. So on carbon 2, I'll have a methyl group. And now the question becomes, how do I deal with the R? First, I need to identify which carbon is my stereocenter. It's going to be carbon 2 because that's the one that's bonded to 4 different groups. And if I look at my groups in terms of priority, bromine is going to be highest priority. Carbon bonded to bromine is going to be second highest priority. And then the other carbon of the chain is going to be third highest priority. And then the methyl group will be fourth highest priority. So from 1 to 2 to 3, I would be going counterclockwise. If I'm going counterclockwise and I want this to be R, that means group number 4 has to be coming towards me. So I can fill in this methyl group as being wedged, and then I can change this bromine to being dashed. All right, so naming alkyl halides, that's just a review. The meat of this module is going to be really how do these things react, but it's always nice to review. We got a little naming review, we got a little stereochemistry review in there. So from there, we're going to move on to starting to talk about reactivity. Okay, so moving on to the main event, what these modules are all about is reactions of alkyl halides. So anytime we approach a new functional group and we want to think about its reactivity, we're going to ask ourselves, what are the frontier MOs? That would be the highest occupied molecular orbital, lowest unoccupied molecular orbital. So for an alkyl halide, our highest occupied molecular orbital would be the lone pairs on the halide. So that would be lone pairs on X, whatever X is. And then our LUMO is going to be sigma star CX. Now remember, sigma star is going to have a bigger lobe on carbon. So sigma star will always lie outside of the two atoms that are bonded. It'll have opposite phases on the two sides, but the big side will be on the less electronegative atom, which in this case is carbon. Now, it turns out that halogen lone pairs, when they're neutral, are not particularly good donors. We will see in organic chemistry a few cases where these neutral halogen lone pairs act as donors, but those circumstances are usually pretty rare. They're usually when they're reacting with something that has a vacant non-bonding orbital, something that's a very good acceptor. So these are not great donors. Where the action is going to be is with sigma star CX. This is generally a very good acceptor. And that's because halides have very low energy, very high electronegativity, which means these orbitals have very low energy. One thing I'll point out from the start is that fluorine usually is in its class by itself. We could have a separate conversation about why fluorine behaves differently from the other halides, partly because it has a similar size to carbon. It makes a much stronger bond, and so usually that carbon-fluorine bond is harder to break as opposed to carbon-chlorine, carbon-bromine, carbon-iodine. So for most of what we talk about, we'll be focused on chlorine, bromine, iodine as our halides. So there are going to be two categories of reactions that alkyl halides do very readily. One would be a substitution. Okay, substitution just means we're adding in some group. We call it Y here, and it essentially replaces X. Okay, so substitution makes sense, where we just replace what we're looking at. The other possibility is what we call elimination. So in an elimination, X is leaving as well, but instead of Y taking its place, Y is going to combine with a hydrogen from next door, and essentially eliminate H and X at the same time from the molecule. So that will lead to an alkene as a product. So when we see an alkene as a product, it was probably an elimination. For substitution, we'll see there are lots of groups that could be Y, so we can actually take an alkyl halide and turn it into lots of different things depending on what we substitute. But elimination always makes an alkene. And we'll learn two types of each, two substitutions, two eliminations. They have these names, SN2, SN1, E2, E1. Essentially, all of module 20 through 23 are going to be about distinguishing between these different reactions and explaining why one reaction type would happen in a given set of circumstances. So we're going to focus on them one at a time. In the lecture, I'm actually going to focus on them in this order. I will do SN2 first. I will do SN1. I will do E2 second, and then I'll do SN1 and E1 kind of together. The way they're numbered in the modules is actually module 20, module 21 is E2, and then 22 is SN1 and E1, and then module 23 is about putting it together. So the order is a little different. So I would recommend that you kind of do module 20 on its own, and then 21 and 22 you can kind of put together. So that's the layout of where we're headed. We're going to start by talking about the SN2 reaction. It might be the easiest reaction for you to understand of all the reactions that we cover in organic chemistry. It's maybe the simplest in terms of donor orbital, acceptor orbital, and understanding what the outcome is. All right, so the SN2 reaction. You are going to have an alkyl halide as a starting material. And then you add something that's going to act as a nucleophile. We'll talk about what nucleophiles we can use. Turns out cyanide CN- is a really good one. It's got a high energy lone pair because it's on carbon. And so what it's going to do is donate that lone pair into sigma star CBr. That's going to break the CBr bond. And what we're going to end up with is a nitrile. And the Br minus will leave. Okay. So our product is a nitrile. And then the halide, this is acting as what we call a leaving group. We will see there are some other leaving groups besides halides, but we're going to start by just saying our leaving group in the SN2 reaction is going to be a halide to start. All right, so if we think about the orbitals involved, my carbon lone pair is going to be an sp hybrid orbital, like that. That's where my electrons are. My acceptor orbital is going to be sigma star CBr. So notice that the carbon has to come from the opposite side from where the bromine is. Okay. Um, the nucleophile, which I'll just call Nu, must attack from the opposite side of the carbon from where the leaving group is. We say that SN2 occurs with a backside attack. That's going to have some implications that we'll talk about in a minute. Some of you may not have had AP chemistry, so you may not know what I'm talking about when I say the rate law for a reaction. You can essentially ignore this part, but it helps explain how we know that this mechanism works and why it's named the way it is. So this is called an SN2 reaction. The N there stands for nucleophilic. The 2 stands for the fact that there are 2 molecules involved in the slowest step of the reaction mechanism. So our reaction mechanism in this case is just a single step, and there are 2 molecules involved. The way that manifests itself, if you have had AP chemistry, you might recognize this. Our rate law would be rate equals a constant times the concentration of the alkyl halide times the concentration of the nucleophile. So the 2 is because this is considered a second order overall reaction, and that's why it's named that way. The fact that we can experimentally show that this rate law matches the rate law of the reaction gives us evidence that this is the mechanism that it follows. So I would say you can ignore this question of why it's called an SN2 reaction. The 2 is just saying 2 molecules in the rate law. All right, I mentioned that there was a backside attack. The backside attack has stereochemistry implications. So because my nucleophile has to attack from the opposite side of the leaving group, what that means is the carbon that we're attacking is going to have to do something we think of as an umbrella flip, where notice as my nucleophile is coming, we have my 3 substituent groups all pointed to the left in this case. As the nucleophile comes in, those are going to have to slide over as the leaving group leaves, and they'll all be pointing to the right afterwards. Okay? We call this an inversion of stereochemistry. So if I wanted to draw the product of my reaction up top, now I'm going to have my SH on the left. My 3 substituents have all slid over and are now pointing to the right. The one coming out of the board or out of the page is still coming out of the page. Right? So this is my long carbon group. What is this? C6H13. My hydrogen is going back into the page still, and I have a CH3 group here. The stereochemistry has been inverted. If I assign R or S to the first one, I have high priority 1, 2, 3 clockwise with hydrogen going back. So this starts as R. Notice in my product, now I have priority 1, 2, 3. I'm going counterclockwise with hydrogen going back. And so that looks like a G. I'm just going to replace it with a spiral. counterclockwise with hydrogen going back. So now my product has S stereochemistry. Um, so this this is what we mean by inversion of stereochemistry. Um, it's true that on rare occasion, if the nucleophile and the leaving group don't have the same priority, in this case, both the nucleophile and the leaving group were priority 1. Um, so we saw a flip from R to S. Um, there might be cases where you don't flip from R to S, but those would be pretty rare. But the stereochemistry will always invert in this way. So it has to happen this way because of the backside attack. So the nucleophile can never come in and just replace the leaving group on the same side where the leaving group was. It has to go to the other side. So anytime you have SN2 happening at a stereocenter, consider that there will be inversion. That's an important part of the mechanism. All right, it's important to consider how fast this reaction might happen. And because we have to attack from the backside and because we are donating to sigma star CBR, we have to ask the question of how accessible is sigma star CBR? And what we're going to see is having other groups near that sigma star CBR orbital is going to make this reaction harder and therefore make it a lot slower. All right, so on this page, we've got a whole series of different alkyl halides ranging from, in this case, a methyl halide to a primary halide. Primary because there's one carbon group here, to a secondary halide because there's 2 carbon groups here, to a tertiary halide where there are 3 carbons. And you can build a model of these to prove this to yourself, but as you add more carbons next door to the halide, sigma star gets harder and harder for the nucleophile to get to. So I'm going to use orange to represent sigma star. In the case of the methyl halide, this is on the right, we have the view of the target. View meaning we're sort of personifying the nucleophile and saying, what does it see as it approaches sigma star? So that red atom on the other side, that would be your bromine atom bonded to the CH3 group. In the case of the methyl halide, sigma star is this big orange target here. Which is very easy to get at. When I put a methyl group next door, that methyl group kind of closes off part of my target. The methyl group is in the way. So sigma star CBR becomes much smaller, much harder target to hit. If I add a second methyl group, sigma star CBR becomes even smaller. When I add a third methyl group, sigma star CBR becomes this tiny dot that is kind of stuck in between all these branches of a tree that are really hard to get to. Same thing is true if we have lots of carbons branching out at a neighboring carbon. So notice in this case, this bottom case, I have lots of carbons branching from the neighboring carbon. This is often referred to as what we call beta branching. That would be a naming system where we call the carbon with the alkyl halide, we call it the alpha carbon. and we would call this the beta carbon. So this phenomenon where you have branches at the beta carbon, this is known as beta branching. All right, and beta branching slows the reaction down. So this middle column of the chart is essentially telling us, all right, how fast can this SN2 happen? And we see that with a methyl halide, it is extremely fast. So it's 18,000 times faster with a methyl carbon than it is with a secondary carbon. Secondary carbon is here our reference where we're saying the rate is 1. At a primary carbon, it's 128 times faster than at a secondary carbon. At a tertiary carbon, the rate is essentially 0. So one takeaway here is you can never do SN2 at a tertiary carbon. And we can do it sometimes at a secondary. There it's pretty slow, but it happens. At a primary carbon, it's pretty fast. At a methyl carbon, it's very fast. But at a tertiary carbon, it'll never happen. And then we also see that beta branching has a slowing effect, which is why this last case where you have all that beta branching, that SN2 is relatively slow. It still happens, but it's relatively slow. So one of the things we're going to consider when we want to do an SN2 reaction is these are what we refer to as steric effects. If it's methyl, the sterics are great. SN2 is definitely a likely reaction. If it's primary, SN2 is still a quite likely reaction. If it's secondary, SN2 is just okay. If it's tertiary, SN2 can't happen. So this is one of the considerations every time you're thinking about an SN2 reaction. One of the things you want to consider is the steric effects. All right, so moving on to think about other factors involved. I mentioned that we need a good leaving group. At this point, the leaving group for us in an alkyl halide, in an SN2 reaction, is going to be usually Cl minus, Br minus, or I minus. Okay. In module 23, we'll talk about how this leaving group, a sulfonate group, might act as a leaving group. So this comes up later. In module 22, we will talk about water as a leaving group. For now, we're focused on chlorine, bromine, iodine. If you think about what makes a good leaving group, you'll notice I gave you pKa values here. The reason pKa values are relevant, you can think about an SN2 reaction sort of like an acid-base reaction. So if you go back to module 12 and think about acid-base reactions, we had like a base reacting with an acid, and essentially the pKa, the lower the pKa, the more likely this reaction was to happen. In the case of SN2, we have nucleophile and we have a carbon. But essentially, A is getting kicked off by itself again. And so if A is likely to be a good leaving group to hydrogen, it's also likely to be a good leaving group to carbon. So a low pKa of the conjugate acid makes for a better leaving group. Um, I see I have this old question here. Is the leaving group involved in the rate limiting step? I'm going to just eliminate that because I don't think it is all that helpful for our purposes. But the key is I want you to know that a good leaving group has a low pKa. So things that have positive pKa's of their conjugate acids, like F minus or SH minus, CN minus, these are not good leaving groups for SN2. So these won't do SN2. You might see them act as leaving groups in future reactions, but those will not come up now. So any of these here, they might be leaving groups in future reactions, but not in modules 20 to 24. The kinds of reactions where they'll act as leaving groups would be reactions usually involving carbonyl groups. So those would come up later on down the road. So for now, we're focused on our leaving groups being iodine, bromine, chlorine, and then I'll talk about sulfonates and water later as leaving groups. So then the big question that remains is what kind of nucleophiles can we use? And it turns out this can be hard to predict. You should know a few general things about good nucleophiles. So nucleophiles generally are going to have a lone pair. And the higher in energy that lone pair is, the better. So they should have a high energy lone pair. So what would make a lone pair higher in energy? Think about it for a second. Higher energy lone pairs would mean low electronegativity. It would mean having a negative charge. Those are things that help make things a better nucleophile. So if you look at this list where you have your better nucleophiles at the top, and then you have some in the middle that are like good nucleophiles. These ones that are listed as fast, those are good nucleophiles. As you get down to the bottom, they get worse and worse. So these down here would just be okay to poor nucleophiles. So notice the ones at the top, they all have negative charge, which makes their lone pairs higher. Notice the ones at the top have carbon with a negative charge, so really high energy lone pair. Then you see sulfur, iodine, oxygen. So things with higher energy lone pairs are generally better nucleophiles. We will focus on just the things in the best and the good categories. So just the ones at the top of this list, down to about ammonia, we're going to consider as being decent SN2 nucleophiles. So we want to consider what are the results of using each of these groups as a nucleophile in the reaction. So that's where I'll head next. So let's start looking at the various reactions that result when we use these different nucleophiles in an SN2 reaction. This is going to be relevant to us because I said that an alkyl halide we can turn into lots of different things, which as an organic chemist is a thing of beauty, because organic chemists are in the business of creating new molecules. So when you have an alkyl halide, the fact that we can use all these different nucleophiles in an SN2 reaction means that we can create lots of different new molecules. We're changing one functional group into a whole lot of different options. So for each of these, I'd like you to pause the video, draw yourself the curved arrows, and then draw yourself the product. Try and name the functional group that's represented by the product. So you pause, and then I'll do it. I'm interested in what percentage of you actually paused the video and what percentage just continued, but it's your choice. I have no control over that. If you haven't paused, I'd recommend that you do, and you do this practice for yourself, because I want this mechanism to be second nature to you. So in each case, the curved arrows look the same. And when we think about our products, in the first case, what I have is a nitrile. So I can turn an alkyl halide into a nitrile. In the second case, I make an alkyne. Now, one thing to note about both of these, first of all, a few things. You haven't necessarily seen this ion before in the second case. This we call an acetylide ion. You have seen it back in Module 12 when we talked about acid-base reactions, and I'll talk about how we generate it using an acid-base reaction on the next slide. But I do want to point out something that's useful about both of these first two reactions, and that's we are making a new carbon-carbon bond. New carbon-carbon bonds are like the holy grail of organic chemistry, because they can be hard to form, and most of the times when we're synthesizing a new molecule, the carbon-carbon bond forming steps are the key steps to consider. So this is an example of a reaction that forms a new carbon-carbon bond. I want you to highlight that in your brain. So we can turn an alkyl halide into a nitrile. We can turn an alkyl halide into an alkyne. We can also turn an alkyl halide into a thiol, or a sulfide. This is where naming the functional groups becomes useful, because if you know the names, it becomes easier to categorize our products and then think about where they came from when we see a novel product. All right, this reaction where we use iodide as our nucleophile really just trades one alkyl halide for another. This one is not usually useful, because we start with an alkyl halide, we end with an alkyl halide, because there's no change in functional group. There might be rare occasions where we use this, but it's not a thing that's generally important in our toolbox. So we will kind of ignore this one as a possibility. Okay, next one, I'm replacing the Br with an OH, so that's making me an alcohol. All right, so this gives me another option to make an alcohol. You may remember when we studied alkenes. We saw ways that we can turn alkenes into alcohols. Now we have another way to make an alcohol. If I replace an alkyl halide with an OR group, that makes an ether. Hopefully you recognize that the next one is also useless because it's, again, not really making any change, so this is not useful. And then lastly, all right, we have this weird ion. We call this an azide ion. And we can replace a halide with the azide ion. So this would be called an alkyl azide or an alkyl azide, depending on who you talk to. This is usually not a final product. These things are very reactive. So oftentimes we will replace an alkyl halide with an azide, and then there'll be some subsequent reaction. I'll show you in a little bit what we can turn this into that might be more useful to us. So this is not usually a final product. But it can be a useful intermediate in a synthesis. All right, so we've just outlined a way to take an alkyl halide. You remember in modules 15 through 19, we saw that we can turn an alkene into lots of different things. Here we're seeing we can turn an alkyl halide into lots of different things: nitrile, alkyne, thiol, sulfide, alcohol, ether, azide. So 1, 2, 3, 4, 5, 6, 7 new functional groups that we can make from an alkyl halide. All right, so that can be helpful to us. The next question is, how do I make each of these different nucleophiles? So, these are the nucleophiles that'll do the SN2 reaction. Somehow I need to generate these different nucleophiles. And it turns out some of them are quite easy and some of them are more challenging to generate. So for example, the easy ones are the ones that we can just buy as salts with sodium or potassium. The key is that when you dissolve a sodium salt, generally it will split up into its constituent ions. So you dissolve NaCN, it splits up into Na plus and Cn minus. You dissolve NaSH, it'll split up into Na plus and SH minus, and so on. And generally, you may remember that ions like sodium and potassium tend to be what we call spectator ions, meaning they get dissolved in solution and all they do is stay dissolved. They don't take part in most reactions. So if I want to use Cn minus as a nucleophile, I can just choose its sodium salt, or SH minus as a nucleophile, I can just choose its sodium salt and dissolve that in solution. Same thing goes for OH minus. I can use KOH or NaOH. It'll have the same effect. For azides, I can just choose the sodium or potassium salt. And again, these positive ions are just going to be spectator ions. And as organic chemists, in a lot of scenarios when we're writing out reactions, sometimes we will include those positive ions and sometimes we'll just leave them out. So for instance, these two things would mean the same thing. If I wrote a reaction this way with NaCN, or if I wrote the reaction with Cn minus instead, those mean the same thing. It's just a matter of, did I include the spectator ion or not? So one of the skills that you want to have is being able to see those two things as equivalent from an organic chemistry perspective. Some of those so that accounts for some of the nucleophiles. Let's see, I'll check off the ones we just addressed. We address CN minus, SH minus, um, you know, often SR minus too, OH minus, N3 minus. So those we can make, those we can just pull off the shelf. There are some that are a little harder to make, or things that you can't just buy uh, off the shelf. But what you can do is create those nucleophiles using acid-base chemistry that you already do know. So for instance, if I have an alkyne, we would call this a terminal alkyne because the alkyne's at the end of the chain. If I have a terminal alkyne, I know that the pKa is about 24. If I can use a base that has a higher pKa than 24, I can effectively remove that proton from the end. So it turns out if you go to your pKa list and you look for, well, what's above 24, we can use NH2 minus as a base. That will do an acid-base reaction. To make this acetylide ion and NH3. You may recall that the pKa of NH3 is roughly 35. So the K value for this reaction is about 10 to the 10th or 10 to the 11th, which is really big, which means if I carry this reaction out, I will make pretty much 100% of my molecules into the acetylide. So if I want to use an acetylide in my reaction, that's how I'm going to generate it. I'm going to react it with NH2 minus or NaNH2. Again, I might include the counter ion and write NaNH2, but I recognize that the Na plus is just going to be a spectator. So to make an acetylide ion, I would use a terminal alkyne reacting with NH2 minus, and then I could use that acetylide ion in a subsequent SN2 reaction. For a thiol, if you look at your pKa list, your pick sheet, pKa of that is about 12. So if I want to turn that into what we call a thiolate, so this S minus species, this would be called a thiolate ion. What I need to do is choose a base that is a bit stronger than that. So I can just choose OH minus. Again, that'll do an acid-base reaction. That makes my thiolate, and it makes water. Remember, the pK of water is about 16. So if I have a pK of 12, pK of 16, the K for this is about 10 to the 4th. Again, that's a big value, so it's going to turn almost 100% of my molecules into the thiolate, and I can then use them in my acid-base reaction. All right, then one more. So I've covered how I can make thiolate. One more I might want to make is this RO minus ion. We call this an alk oxide. An alk oxide because it's an alkane with an O minus. And if I want to make an alk oxide as my nucleophile, I will use an acid-base reaction, but I'm going to use a different base. This is a base that you haven't seen. The hydride ion in NaH. So NaH is going to split into Na plus, and H minus. You are likely never to have seen H minus before in your chemistry career because this is a very strong base. This hydride is a very strong base. This hydride is very effective at finding the most acidic proton in whatever it's reacting with. It makes your alkoxide in this case. And the other product is H2. You might know that H2 is going to be a gas. So it's going to bubble right out of your solution. You want to be careful when you do this because it's an exothermic reaction, releases a lot of heat, and produces hydrogen gas, which can be a recipe for explosion, which is why you've probably never encountered hydride in the lab before. But it's very effective at deprotonating the alcohol and making the alkoxide, which we can then use as a nucleophile in the SN2 reaction. So I've covered how to make each of these nucleophiles. So SN2, just to reiterate some key points, it's a very versatile reaction. All we need is a good leaving group on our carbon and good sterics. So usually a primary or a secondary alkyl halide as our starting material. We can react with a variety of nucleophiles and produce a whole bunch of different functional groups. So now you have the tools to create all the nucleophiles you need and then use them to react in an SN2 reaction to make a whole bunch of different functional groups. So you have just learned a very powerful tool. Before I close this portion, I do want to address one of the nucleophiles I didn't discuss. So you'll notice down here, ammonia is a very good it's a good nucleophile. It's the only one in that good nucleophile list that's actually neutral, but I didn't discuss it on this page as a nucleophile that we would use in the SN2 reaction. So I want to talk about why. Turns out ammonia is not a great nucleophile for SN2 because it tends to do a thing we call overalkylation. And here's what I mean by overalkylation. Ammonia can react with an alkyl halide. That's true. And that will make this ammonium ion and some bromine. Okay. But then that ammonium ion can get deprotonated by another molecule of ammonia. Which makes this amine, which is also a good nucleophile. So if I have another molecule of alkyl halide around, this amine can go ahead and do SN2 as well. Now I've got nitrogen bonded to two ethyl groups for my alkyl halide. I can repeat that process a couple more times until I'm left with nitrogen with 3 of my alkyl groups. That can go ahead and do one more SN2. So this process repeats until I get this final product, which We call this a quaternary ammonium salt. All right, why would I call it quaternary? Because that nitrogen is bonded to 1, 2, 3, 4 carbons, so it's quaternary. Um, and it's ammonium because it's got a positive charge. So for that reason, we don't often use NH3 as a nucleophile in SN2, but we do have another workaround. So it turns out if I want to add an NH2 group to a carbon, I can use the azide as an intermediate. So I can react sodium azide. Now remember, this is going to be Na plus and N3 minus. The Na plus is my spectator, so I forget about it. My N3 minus does the SN2 reaction to produce an azide as the intermediate, and it turns out that our old friend H2 and palladium, which we saw can hydrogenate an alkene, turns out this is a very versatile set of reagents, and this will turn your azide into a primary amine. So if you ever want to make a primary amine, you can use the azide as a nucleophile in an SN2 reaction, and then use this catalytic hydrogenation to reduce it to an amine. So NH3, this is not really useful for us, but we have a workaround. It's just a couple of steps. All right, let's close by summarizing what we've said about SN2 reactions. So remember, the mechanism involves backside attack. So that means you've got your alkyl halide, you've got your nucleophile. It's always just 2 arrows. You have the lone pair donating to sigma star CBr, or sigma star CX more generally. Stereochemistry, you invert the stereochemistry at the carbon where the reaction happens. For it to be rapid, you need to have sigma star CX accessible. So methyl is great, primary is good, secondary is okay, tertiary can't happen. You need a good nucleophile. And you can see the list for which nucleophiles are good. And you need a good leaving group. So at this point, that would be Cl minus, Br minus, I minus. We'll see something called a tosylate later. So that would be OTS. Or water as your leaving group. So that's your summary of the SN2 reaction, and that is essentially all of Module 20.